So it's a great pleasure, to give a talk here. And so I mean, my originally the title is how to break electroweak symmetry naturally. And eventually we actually find an enhanced global symmetry, which we call it the maximum symmetry. And they can really have a lot of fancy latent, behaviors. And really helps for instance, a model for the composite Higgs. But in principle, this can be, added to any kind of models where Higgs is essentially a pseudo-lambda closed boson. And this is my work with Chavataki, with organizer here, and Ken Mark with my postdoc, and there are several other papers we are coming out soon. So basically, we are just particle physics, and we want to ask, what are nowadays the core questions we want to think about. So once we think about, I would say, it's the origin of electroweak symmetry. And we know that Higgs is important, and the Higgs mechanism is the core to have the standard model. And we are just, using colliders to check the standard model again and again. And to some approach, seems everywhere we are just asymptotically approach the standard model. However, there's one thing actually we make stay in the textbook that has never been really tested before. That is the Higgs potential. And this simple formula at the very beginning is just use the simplest non-linear potential, where you basically just formula the series is normalizable and also analytical at the tree level. However, since this can only be tested actually by things like the Higgs self-coupling or something like that, which you essentially test the local behavior of this value. But on the other hand, one never actually test the global behavior of this potential. So in the future, on one hand, the colliders, we probably can test those things, to the 3 powers indirectly or directly, or even 4 powers probably only indirectly. And these are actually one of the, I would say, the key essential things for the future practice. Of course, one can also tackle those things globally. And since, for instance, the gravitational waves of the phase transitions. So it's interesting. And here, mostly, I just wanted a simple question. In the future, or probably we actually may know that if there are some deviations or something, whether or not, I'm just curious whether those in diagonal potential looks like this or not, and how they are actually generated. And now, why we should think about the case where Higgs is essentially a pseudo-lambda Gaussian boson. Well, there are many reasons, so I just list a few which I think is more or less most important. Well, first, it does have the original electroweak symmetry breaking. The Higgs potential is calculated. And also, because Higgs is a pseudo-lambda Gaussian boson, so your Higgs mass is essentially much smaller than the confinement scale. Where at the scale of the confinement, there are many other kinds of deviations which essentially will spoil the electroweak precision test. But one thing you keep in mind is that this actually the symmetry breaking decay constant is still might be much bigger than our electroweak symmetry breaking scale, and this gives another tuning of so-called little hierarchical. Well, definitely, besides the mechanical generated potential, also the just actually in front of experimental test. One thing we actually in the past has been emphasized again and again is the gauge hierarchy problem. Well, if this pseudo-lambda boson is coming from G mod H, well, this actually gives us some confinement or something. So in the end, actually, our fundamental scale of M band goes to this lambda of 4 pi f and becomes small. And then there is a question that for this lambda and how they actually go into our electroweak scale. This is not actually automatically solved by the things like composite Higgs, but can be solved, for instance, in the maximum symmetry limit or in some other mechanisms in the old days, like the deconstructions or something. And this is slightly more than the fact that actually I just care about this model has one tuning, I have a 0.1 tuning or 5% of tunings. I mean, it's slightly important that the reason that it makes the model actually predictive at IR. In a sense that, suppose I have a potential like this, and I say that, for instance, a lambda equals 4 pi f. But this lambda equals 4 pi f is just a very, first order rough estimation. In principle, I can do this absolutely fine. But if my potential is highly fine-tuned and they are super sensitive on the results that has a lot of cancellation and other things, the potential will just look like this and there's low electroweak symmetry rate. And the two actually can share just the same IR parameters, for instance, M rho, M F, C, left, C, right, for the mixing of the two partners in that. So, although that in my eyes there is no guarantee or something that forces us to make our electroweak symmetry potential that the quadratic divergence or log direction are regulated by the two partners or something, they may just have some UV dependence. But if you want your theory to be, checked and see and IR predictions, I think it's still much better that you make a potential completely fine and irrelevant of the physics at the scale of lambda, at least for the calculation of the Higgs potential. Okay. Wow, this one is too heavy. So there's another thing I want to just slightly emphasize, but that model is in that has especially because the Higgs is a pseudo-lambda Goldstone bosons. The lambda Goldstone one has derivative coupling, so basically, I mean, they are the universal behavior of the Higgs couplings. And in a recent paper, actually, modified. In a recent paper by, for instance, Yan No, actually, this was also pointed out from the soft pi theory. So in the end, there's all of these modified Higgs coupling at the leading order level. They just follows completely from the symmetry breaking scale. Nothing else, even irrelevant of the fact that for the symmetry group, only the coefficients in front of the Higgs, but you can redefine everything by that.
You are talking about Higgs coupling for double levels, right?
Yeah.
Only about this.
So basically, I mean, after this, we should think about, for instance, what are the, the things in our nature, which, for instance, is the pions. Pions can get their mass actually from the two sources. So one is actually the parton masses. Well, your pion mass actually goes like mu plus md and there's another one which is that the splitting of the pion and the neutron and the charged pions. These are the quantum corrections, which give the splitting of the neutron and charged pion. And this is the U1 electromagnetic calculation. And for this, in principle, one can also build up composite Higgs models based on that, but up to now, only models actually the four fermion depend the bosonical, tightly colorful like models, which there are some models, for instance, even like Adam Martin has a paper on that. But mostly they are just the patterns only tightly colored. And also then there are the other thing which is they are purely coming from the they're purely coming from the quantum interaction like the top part. And if they are purely come from the quantum correction, so I ignore the tree-level mass coming from the atoms, which will be the one that I was just talking about. And usually the top part will be the main source. So I talked about the good side of this composite Higgs model, where Higgs is stable and the Goldstone boson. But right now, there are still some challenges for the models which I will point out. So, unlike the pions, essentially you just get a super easy potential which is quadratic. Now you should have things called the vacuum misalignment, that actually they have a web that they can develop a vacuum which are non-zero. And essentially this is our vacuum expectation type.
Too much force.
Okay, so I probably should have practiced this before. So basically saying that in order to get the correct model, one has to first make sure that you get the correct electroweak symmetry gradient. Make sure that your potential actually looks like this. The other thing that you need to get the 125 GeV Higgs mass. And this is not trivial in the sense that our top part mass is too heavy. So usually you get a 300 or 400 something because the M top is large. And also if you have a model which is kills of the UV divergence, then it's good. And also we should actually kill out all of this so-called the technical tuning. That you, in the end, you tune your model so your potential has such a deformation. In the past, actually, for instance, for models like deconstructions or little Higgs, for instance, like there are several, very nice mechanism of those things, but there are also, have its own drawback. For instance, the deconstructions, if you have a finite potential, you basically have three sides, which is fine, but on the other hand, it does make the model slightly complicated. But they have this so-called double tuning, which I showed you before. Still, the technical tuning is large. They also didn't give you the correct Higgs mass unless you tune the model, which in the end they approach that maximum symmetric mean.
So what do you mean by technical tuning?
Yeah, I will talk about that when I talk about the potential. And also the twin peak is also a very nice one, especially we don't search the colored particles. And but on the other hand, they also have some difficulties in the model building. Which in the end I will mention that the maximum symmetry can also greatly help the twin peaks model. And also the other thing that I want to say that there's actually this general mechanism that one can play based on the symmetric process space. By doing that, actually, in the end, the formalism actually this symmetric process space will give you a direct Lagrangian that connected to the Higgs potential. They also will directly, since it's an effective theory Lagrangian, they also can directly go to your phenomenology. So in the end, one can now really establish a direct link between what is the the UV divergence, all of those sensitivities, UV sensitivity of the Higgs potential to the phenomenology that you will see in a very unified and model independent manner. So let's just first talk about what is the symmetric Coset space.
So this is an extension of previous theories regarding custodial symmetry to protect T parameter?
No, not at all. It is actually the new symmetries that are applied to any kind of symmetric Coset space, but on the other hand, it's not used to things like precision or something. It's used mostly to basically kill some of the form factors that are theoretically very troublesome. Mostly, for instance, they have the quadratic divergence. They have this, they always make the mass term too large that you never get the correct Higgs potential or something like that.
But what's different than doing the low energy analysis of the Higgs at Higgs effective field theory at 6 dimensions?
Yeah, I mean, in principle, I can just write, just for instance, write a general low energy Lagrangian. I choose the exact, the parameters that I have. There's no problem for that. But on the other hand, as I have emphasized, for instance, you then, in order to get the correct electroweak symmetry breaking, your parameter becomes super fine-tuned. Probably you say, yeah, I don't care about fine-tuning, even a single point in my model works, then I don't care. But on the other hand, as I emphasized that if your potential are just super UV sensitive, the essential cutoff is not something that really you can predict. It's just roughly 4 pi f. By changing this 4 pi f to 4 pi minus 0.1 f, the shape of the potential completely changes. You lost your theory of the IR prediction. And also, this is just from the technical point of view, from the most model builder point of view, that one still need to establish this, for instance, quadratic divergence and other issues. So, but in the end, I also commented it does have a lot of phenomenology, implications. It's not something up in the air. So let's first have a symmetric Coset space. So symmetric Coset space is basically, let's say my TA actually is the H and my TA hat is the broken generator actually. So symmetric Coset space is something that so these two commutator relation jump from the fact that H is a closed group. There's another important thing is actually this two broken generator actually gives you an unbroken generator. If this is true, this is called the symmetric Coset space.
In the first one, you mean that TA equals TA?
Yeah.
Oh, sorry. Yeah. And the important thing that there is an automorphism one can define. So here we can say that there's an automorphism. So let's say this automorphism I will call it V, and it's essentially the Higgs parity operator. So the unbroken generator doesn't change, but the broken generator actually has a minus sign. And this automorphism of V actually in our real world is actually the Higgs parity operator. For instance, the pions which decays into 2 photons, that's precisely the normally actually break this pion parity. And this pion parity, since here I call the Higgs parity, is completely this automorphism that map that one can have. And also I want to emphasize that although I say that I imposed everything in the symmetric Coset space, but symmetric Coset space is almost everything. It actually contains almost whatever we are essentially care. And also there are other models which are slightly different, but they are not completely symmetric process space, but as long as your Higgs is, is in this incomplete process space, you can still use those things. For instance, so it almost contains everything. So here, I mean, some of the group I have to change the dagger into a transpose, depends on its real or something. So, and this V is important, which I call the fixed parity operator. So the thing that usually, I mean, when we describe those goldstones, we don't care about the radial direction. So in the end, I mean, usually we just completely forget our radial direction and then write the goldstone dynamics in terms of those exponential matrix. And those are something which people always use. For instance, define a matrix U. I mean, one can write everything like this. Is mostly I essentially, I mean, kill all of the radial direction. And this goldstone matrix, I mean, in the G model, the general formula, they transform like this. They transform like actually the GU H dagger at H is a nonlinear function of this goldstones and also the G transformation. So because this is a complicated function, that's why some people call it the nonlinear formula. But importantly, since if I have the symmetric process space, everything can be written in the transform linearly on the G. So basically now I define this to be the UD dagger. And they just transform as the G sigma prime G dagger. And you may feel confused, I mean, then I have everything in G, where is the information that G spontaneously breaks into H? The one is that actually this information is encoded in the V. So G actually breaks into H is encoded in this V. As an example, for instance, let's say FO5 mod SO4, which is one of the most common used process, this V is actually, as you can see, this V actually already just have all the information that G spontaneously breaks into H. So now, just armed with all of those things, which look simple, now we just apply everything, for instance, for the Higgs and torque system. And I can just embed our standard model fermions, for instance, in the minimum composite Higgs model, for instance, just like this. And they just have this, some people call it the Spurrier symmetries, which they still transform, again, linear. These Spurrier symmetry, they are not really the symmetry of the standard model, but they are essentially the one that when you integrate out the composite states, the symmetry that the composite states have, which are essentially will transmit it into the low energy Lagrange. So now I mean I can write a torque Higgs system, but remember that actually this thing on prime equals 1. So the most general low energy Lagrange I can write down is So I have several formula on here. And this is, I would say, one of the most important master formulas that one actually has. Why that? So first, let's say, so actually this sigma prime, actually the square equals 1 is very funny. So in the end, everything of expansion of this sigma prime stops at the linear order. And also in this, because basically, I mean, this is basically this spurion, encoding is actually, the first piece to 0. In principle, actually, for the sigma prime, the nonlinear, the Lagrangian actually expanded over the derivative powers. However, all of those derivative powers, they never contribute to the Higgs potential because, it's a derivative of the Higgs. So in the end, that all of those things, they are irrelevant, but they are actually relevant for all of these Higgs Z and all of those couplings. And then everything now you can see that the overall sum normalization, you don't probably care that much. That's how the Goldstones actually correct your top kinetic term. The left-handed kinetic term, right-handed kinetic term, and also the master. The other important thing that these actually in principle, I mean, it can be something that you integrate out the top particles. However, in principle, you can also use them to integrate out the scalar particles, for instance, stop, or some other, fuzzy behavior, not really the resonance or whatever. So everything can be encoded here. And they are very generic, for instance, integrate out the stop, something. Anyway. So now let's look at the symmetry of this, Lagrangian. The key observation is that this pi1 form factor is the troublesome piece for everything. As long as this piece is 0, in the end I will show that the potential it has the most simplest structure, and also it just kill all of those, stuff you don't want. And there is indeed enhanced symmetry related to that. And in the end, this is something that, at least for me, in any kind of particle physics before, mathematically, this kind of symmetry prediction has never been pointed out before. So the thing that let's look at, for instance, the kinetic term of this has its own symmetry GL, which basically only the left standard fermion has such kind of, for instance, flavor symmetries. Notice here the Goldstone matrix doesn't transform. And same thing for the G right.
Jing, I believe nobody can read that. You should probably write
Oh,
it
yeah.
down.
So, sorry,
I can read that.
Slowly.
What?
No, what?
I stop? No.
It's okay, it's okay.
Oh,
Now you can switch to the right.
I probably. So the important thing is that if I look at my mass term, if I requiring that my mass term is invariant under such a symmetry, then what happens? If my mass term actually is invariant under some symmetries, so this G left cross G right symmetry definitely is broken by the mass term. But it's not completely broken. There are maximum enhanced symmetries that one can impose so that finally your term actually is invariant. This requires your left-handed transformation, and the right-handed transformation has some properties.
Sorry, what is anode?
Huh? Okay. So you just plug this in and require the mass term is invariant.
What is G right?
So G right is just the unitary matrix which actually transform the side top right, but since the side top right is a fundamental representation of the G. So for instance, SO5 or SO4, this is a 5 by 5 unitary matrix. which is just for instance flavor.
So
You have
it's an element of G.
yeah, exactly. So that's why I write it as the GR. So this I can redefine that my another transformation which is actually, and in the end you will see this redefined transformation is the symmetry of the composite states. And then this actually becomes the GV. So now I consider infinite small transformation. So my GL actually involves a super small transformation of this. Same thing. So just plug it in, I have so now the important thing that you will find that the two transformations, if they are on the broken direction, they are the actual minus sign, which means that it's sort of like the axial combination. While if they are in the unbroken generators, they actually have to transform, on the same way. So it's sort of like the vectorial transformation. So in the end, a very naive picture that one can draw is that because this mass term actually essentially will give you a twisted mass which looks like a big V, and I will show you actually for the composite, for instance, composite Higgs models. Those are just the low energy Lagrangian. So in the end, this goes to, I will call it the GV prime. But essentially it looks like HV and G mod HA. This is the sort of the things that encode the fact that how they actually transform for the two of the father group. So these are the so-called, I would say, the maximum symmetry that leaves my Goldstone matrix or the parity operator invariant. That's why we sort of call it the maximum symmetry. Also, when building models, there are just too many of the little, smallest, simplest mini or something. We go to the other way, so biggest. So now let's look at, for instance, the structure of the potential. I have been telling you probably again and again that this will help for the fixed potential.
Are we still in this SO5, SO4 picture, and this is psi L and psi R, or are we looking at a different Lagrangian?
No, it is this. When you integrate out all of the essential composite states, they give you the low energy Lagrangian, which I write down there. And after I show you the potential, where the potential can be irrelevant to the specific UV completion, then I will give you an example of the UV completion.
What's different than just deciding axial U1 in the low energy theory?
So what's the use of the axial U1?
To count these left versus right transformations.
No, the thing is the following. The thing that first you want to do everything non-linear, because for instance, if we build a model, in the end this is SO5 more than SO4 or something. It's not just a complete U1, right? You cannot build a electroweak symmetry breaking just coming from the U1 group.
No, but I marry a U1 axial with transformations that are non-abelian, and then I get your plus and minus symmetry if I have vector like quarks in the UV theory.
No, why? I mean, here is that it's compact. This has I mean, I will show you later what is the use. But the thing that, for instance, suppose I have actual U1 or actual symmetry, then how do you help for the Higgs potential or something? I don't see any benefits of just adding a actual U1.
You're getting a leading Higgs top interaction where the Higgs does not transform into U1.
So, I mean, if you want, I can talk to you later, but I don't think just imposing a U1 that you can solve everything.
But your generator relations just looks like a U1 transformation.
No, I mean, why this generated relation looks like U1? It's the fact that how they actually have the commutator relation with your fixed parity operator V here. That's essentially probably why you feel it looks like U1, but essentially it's not.
But that's the only thing that lets you have a low energy with left and right chiralities.
Yes?
So it's a U1 actually.
No, because basically, for instance, let's put it this way.
Yeah.
For instance, I have a composite Higgs model where basically my composite fermion, they are in the fundamental representation of the G.
But they come in vector-like pairs with respect to the standard
No,
model.
but as I have said again and again, in the end, this is not just the purely vectorial combination. It's something that twisted, that inherited, collected to this kind of symmetry breaking part. Anyway, if you don't believe me, you can try to just build up one model or just write the mathematical structure. This can be completely derived from U1. If you can do that, then yeah. No? So now let's just look at the essential Higgs potential. So let's say, just for simplicity, because I need some concrete examples. So let's say I use SO5 more than SO4. So in this case, the master formulas actually goes to and just so basically, I mean, the fact that you have something like sine, cosine, or sine 2h or whatever, those are the depend on your symmetric group. That's why I give a complete example.
Could you remember what dV is and dV1?
Oh, sorry, it's a trace.
Oh, trace.
So the Coulomb-Weinberg potential is just because it's a fermion loop, so there's a minus sign. And then the number of degree of freedom for top bucket is 2 and C. And again, we have this, which is probably all of us know, that is actually this trace of the log, something like that. But in the end, since I integrate out all of those things, so the thing that I just have two of these pieces inserted here, and one of these pieces will plug in at the master. Just put everything in. I have again the fixed potential. And just throw away all of the constant piece. Right hand one, I want to write it. if I just plug it in, everything looks like this. So now I will see that suppose actually all of the corrections to the potential, sorry, the kinetic energy is 0. So all of those things you throw it away. And all of these you throw it away. And the log 1 plus 8. And definitely actually this is just an expansion because basically the pole actually always exists.
Sorry, why
Every-
is 0?
Huh?
Why is
Pi one is
Pi 1 is 0, so it's log 1. Okay. So because you can see, it seems everything is just log 1 plus x. That's why essentially how you can do these expansions. So in the end, I mean, by doing these things, just as an approximation, I have a super simple formula. And actually pi 1 is almost 1, so.
Pi 0 sono. Pi 0 sono.
Oh, sorry, yeah, pi 0. So these are the important things that you can see actually in a very compact formula. That is actually the Higgs potential, in the maximum symmetry limit is almost the dependence of the top mass on the Higgs square with some, momentum integration. The M top, as a reminder, is just true Higgs vacuum excitation value is this. So very naively, actually, the Higgs is really just a top mass square to some extent. So now understanding the truth of electric weak symmetry breaking becomes just the sort of even trivial. Because in the fundamental representations, just do some simple projection.
Question. So, what's the difference? How maximal symmetry works if I compare to the normal SO5 to SO4?
I will do that
Well,
when.
in these lines that you wrote, what's
Yeah.
the difference between?
Yeah. That's actually the tuning part that I will talk about. Right now, just wait for 5 or 10 minutes. Okay. I have a few sections for the comparison. So right now it's Right now I just show you the simplicity. So this is just this, and then potential is just for instance the sine 2h square as a minus sign because it's the fermion loop, and this just gives me something like this. Non-Lagrangian potential again. But definitely, then how I can argue that the Higgs potential is finite? It's also very simple because actually this M1 form factor, they come from the fact that for instance composite is my top quark actually mix with my right-handed fermion, while the Yukawa is dimension 1. So I always have something like CF left, C right, F right, so dimension 2, then times the vectorial mass of the fermions. Because if a vectorial mass of the fermion is 0, my potential is 0.
Why is it not H over F?
What is
Where
not
did
H
the
over?
F's go? I
Where?
thought the sign was H over F.
No, well, what is H over?
So SH squared?
Oh, no, there's some other, F normalization, which in the end they cancel when you
That
do.
was the problem of the tuning, no? That you don't want the coefficients.
Right. I was showed before. In the end, the gauge will cancel this part. That's the minimum tuning of this 1 minus KC. The important thing in the normal models, this part is huge coming from the pi 1 form factor. I will show you later. So basically, because of that, just do a simple counting that already have dimension, 3, and this is basically how everything actually goes like. So this actually tells me that my potential is actually the CL square C R square F square, and prime square, really finite. So now let's go to for instance, the most commonly used model, which is MCHM5. So in this case, the fundamental finally the fermion in the fundamental representation actually goes like 4 plus 1. So the other thing I want to mention is that the counting of this type 1 form factor instead, it goes like, for instance, the C L squared F squared. That's it, because they only depends on the CL that they has some couplings. So in the end, the final part is this. After the UV, actually they go like this. So just by doing this, now I can have the other Lagrange. So just from the CCWZ, I forget the kinetic terms which are used this. So I don't mention that part. So the epsilons are dimension 1. So those are the CCWZ that, so this transform as G, this transform as G, U, H dagger, and this transform as H. The important thing is that also the important thing that for the coset space, this 5 equals 4 plus 1 actually has 2 combinations. It can be actually the 5 equals, for instance, let's say I define a psi plus actually equals the psi q which transform as 4 and the psi s. There's another psi minus which actually is psi q minus psi s. Both actually are the good fundamental transformation of this SO5 or whatever. So this property is essentially the fact that you live in a symmetric coset space. And also, again, this psi plus is V psi minus. So now I can choose everything transform on the the representation of H into the representation of the G plus the V. And essentially you throw out, you just integrate out these psi plus, they are completely the low energy Lagrangian that I have integrated now. So the important thing is that I do these combinations and assuming that actually there's another terms which basically have something like so this. So the important thing is that first, my elementary and composite mixing actually respect the full G symmetry. So I just throw away all of those terms. And again, you have this so-called additional SO5 symmetry, which your psi plus L also transforms, which is essentially the G prime that I've been written down before. So now, we can see that how the mass term breaks the symmetry. So slightly from the normal case that I have So these are the SO5, more than SO5 actually breaks into the SO5 factorial. These are the SO5 left, goes SO5 right, goes to the maximum symmetry. And then you have this SO5 left, goes SO5 right. If both mass term is non-zero, they go to the SO4.
What was the first relation that you wrote? The one at the top?
So MQ equals MS. So here you have to flip the sign. So in the first case, I won't go through detail, but the thing that this SO5V actually contains the Higgs shift symmetry. So essentially the Higgs potential is zero. There's another possibility, the twisted mass and this. So I just argue for the structure here. So in this case, definitely, so for instance, if my G left transform as the, so in the maximally symmetric limit, suppose my C plus L equals 0, then they transform like this, while my GL prime actually is the U alpha. When U alpha is the Higgs shift symmetry that one can consider. So just plug it in, you have this U transform goes to U times the U alpha. And then your total potential is invariant under this transformation. So this means that as long as I have a Higgs shift symmetry, I can use this kind of transformation to reabsorb the additional terms, which means that the Higgs shift symmetry now is a good symmetry of the Lagrangian. So C plus 1 equals 0, Higgs shift symmetry is a good symmetry of the Lagrangian, my potential is 0. And also because this C plus in the end, they basically make a closed loop. So every time you actually have both of them. So just by counting this, I have a potential which must look like C plus square F square. By using a very similar argument, I can do other things like again, this just gives me the structural potential, which is essentially what I have been showing you by deriving the low angular Lagrangian, which is the top mass square.
But if your cosine is such a big, shouldn't you have more goals than those ones?
Sorry?
You have twice, right?
Uh,
You break SO5 to SO5.
No, just a minute. The thing is the following. The thing is here, I only use the goldstones, which is spontaneously breaks the original G into H. The additional flavor symmetry that are assigned to only the top left or the top right, they are just explicitly breaking or something. They are not there is a spontaneous breaking.
Are the symmetries of your two-set Lagrangian or strong?
So basically the thing that they don't give you additional goldstones.
And why? What are the symmetries? Are the symmetries accidental symmetries of your two-set
Yes,
Lagrangian?
yes, it's accidental
I think
symmetry
it's
right now.
from some UV calculation.
Yeah, exactly. That is the twisted woods, which I will mention later. But for this setup, we don't do the twisted woods. So I mean, similarly, one can argue that if everything looks like your SO4, then this is basically you do the very similar argument I don't mention. So now let's go to the tuning of the potential, and that I think probably will finish.
Sorry, I got lost. What are the two expressions of V that you wrote?
Here?
Yes. No,
This?
the two. What?
This or this?
Both.
Okay, so now I explain to you again.
Okay.
But just forgive me, I spend more time. So let's say I choose this case, okay? So this is already 0. Now it's basically the argument of collective symmetry breaking. I choose my C plus L to 0 so that the Higgs shift symmetry is a good symmetry of my Lagrangian. Why? Because the Higgs shift symmetry is my this. H go to the Higgs shift symmetry. Essentially my U go to U times U alpha. And then I define my transformation of the left-handed field. This accidental symmetry has this GL prime goes equal to U alpha. And then I define the right-handed transformation like this. You will find that all of the factors coming from the additional this U alpha is absorbed, it's cancelled. So which means that our Lagrangian, the Higgs shift symmetry is a good symmetry. So it's basically like you can absorb the Higgs as just a field redefinition. So in the end, my potential is 0. As I have shown, you have to show a closed loop. So this you have to have C plus square. Similar argument to C plus R square. Similar argument that you must have this has a vectorial map. And then okay. So you use a very similar argument, you can argue that if they break into X04, then this. So now we go to the final part, which is the tuning of the Higgs potential and how compare it to the other models we have. So let's say the Higgs potential, as we can see, is just this. And the difficulty is that we require this constitutive gamma f to be 2 beta f, which is smaller than 1, which means that this term has to be small. The important thing that if you look at this gamma f, actually, they are very troublesome because they are indeed the expansions that are linear under this pi 1 form factor. Well, for beta f, I don't write it down, but they are just high powers. Okay. So the important thing is that as I have do a very simple countings before, so this goes like C plus L square F square P square and equal to infinity, and also the goes to the finite piece. Suppose my MF is basically GF times F. This GF is just I assume that the pole actually almost dominant under the fermion, composite fermions. So basically saying that you put it in their quadratic divergence and then you this in their divergence is just completely huge you are comparing to the other one. So the final tuning is actually this value of the natural size. If you have a quadratic divergence or log divergence, then your first term is always divergent, but the other term is either log divergence or less. So it's much, much bigger. So these are the the tuning formulas which is Panico and Wood, which I changed the epsilon into C. So large. Of course, in models like deconstruction or something, they regulate the UV behavior of the form factor, but they don't really have the finite part to be 0. So if this is regulated for the UV, we still have these issues of extra tuning, which is the double tuning that in the yeah. So the thing, this is basically from the fact that if you naively count using, for instance, all of those form factors, because these you have the form factors, without the extra square. So this contents is always like, as I have shown before, the finite piece actually is always like this. However, for all of the pieces here and also for the data F, they always, the finite piece is actually something like this. And usually the mixing term is much smaller than the vectorial masses. So this gives you another tuning that is usually dominated by this pi1 form factor that always drives your electroweak symmetry breaking to the Higgs limit, which essentially you derive and you get the C maybe equals 3. But on the other hand, it only goes to 1. That's essentially, if you don't have the actual cancellation, that's how it is. So that this is the so-called the double tunings in the composite piece. Besides these tunings in the C, actually, there's another tuning which I have mentioned is the fixed mass. So
At some point.
yeah, it's just finish. So the thing that for us the case is that we have these H contributions. No. And this term is always much smaller because of the G over G rho suppression. So in the end, you use these positive quadratic terms to cancel this actual gamma s. And that usually in the maximum symmetric composite model is this, and in the normal models, which is basically something like this. And we just can also scan, and it's the same thing, that you want to use the Barbieri judicious measurements. So the lattice fixed mass is basically, if you look at the Higgs formula, it's basically so the important thing in the maximum symmetric limit you can see, this term is actually maximum. As I have said before, the reason that one gets too large fixed mass is that the total mass is too big. But we already get this term to be largest. So in the end, this is the degree of the composite, which is the mixture angle. So this mixture angle becomes minimum. The minimum mixture angle gives you the minimum lattice top quark mass, which is and this is always proportional to the fixed mass. That's why in the maximum limit, actually, you get the lattice fixed mass. So finally, we go to the test. There are two kinds of tests. One kind of test that you actually test the model in the most general effective theory. The other thing that you test the model for the tall patterns. So the first test of the model is this pi1 form factor is 0. This test is that actually one can see the high power corrections of the top quark mass, which is actually that the actual small separations. Alpha is order 1 parameter. So this is the famous, 1 square root of 1 minus cosine. And CHM5, for instance. But there are actually high powers of corrections that if this pi1 is non-zero. However, for the group Higgs, these group Higgs actually instead, they just, this is a determinant of the mass matrix, has nothing to do with how you renormalize your zero kinetic term. So they still, group Higgs or still like. So now the test is accurately measure the TD bar Higgs and the group Higgs, and then comparing the two. So it's basically I mean, of course, this is still very, very difficult, but it is claimed that at a 100 TeV collider, that for instance, human claim that can be 1%. So I believe that is one of the places, you know, you can see this very subtle structure. The other thing that we look at core particles. Now, I have derived a general sum rule that is for the So the important thing is that this is the diagonal Yukawa that one has for all the mass matrix for the charge 2/3. So no matter what the representation, whatever it is, you just compute the diagonal Yukawa times their diagonal masses. This also includes the top part, which actually has the opposite sign. So in the end, if this trace is 0 up to the order of V squared over MF squared, then you don't have the quadratic divergence. If there is an additional cubic, this sum rule, then there is no law divergence. So by actually accurate, because this is in the mass eigenstate, so one can really measure this very well if you can actually measure this diagonal Yukawa coupling of the top particle and the figures. So finally, I just give one word for the comparison for the other models which other folk has asked.
Okay, Jing.
Just
Oh, people are getting very hungry in there.
Yeah, say it in words.
Just some words, that's it.
You don't need the blackboard. No, because it is
So-
before.
So basically the thing that the divergence, for instance, for the all of this piece is this pi 1, or for instance, for the deconstructions, one can easily prove that actually this pi 1 form factor for the n side, let's say pi 1, actually goes to p to the minus 2n. So this is precisely that n equals 1, that quadratic divergence n equals 2 is log divergence, and n equals 3 is just finite. However, the important thing is that here, all of the models, they still have the finite, large, these pi 1 form factors. So that's precisely that the model actually is very different from the all of those deconstructions or other things. And compared to the twin peak is actually the funny thing that because as you can see that this is pi 1 sine square pi 1 t cosine square and So if I just don't have this pi 1, then automatically I also have this the same switch symmetry which the twin peaks has. That's why actually for the potential they look the same as the twin peaks for the tuning and but the good thing that here is we don't need this actual soft breaking which are suppressed for the twin peaks, which can only come from the U1 for the most natural case. So in this case, actually you can have a large this contribution from the gamma G that makes the cancellation. So I just stop here, and in principle, no contact. Okay, so people welcome more on the lunch.
One question? No, but yes.
Well, okay. Just,
Careful,
sorry.
people.
Okay. No, just to be clear on the nature of this GL and GL symmetry in that Lagrangian which you had written up. So GL, the symmetry of kinetic term, does not contain any elements of G, right? It's not any part of the electroweak symmetry.
No, it's just accidental symmetry you see from the flavor symmetry.
And does it contain any of the elements of standard model flavor symmetry, such as SUP, quark, or SUP?
No.
Okay.
These are so it's basically here I only apply to the third generation, so it has nothing to do with the actual flavor symmetry. It's only that I have these custodian particles which they form actual You can think them as additional flavor symmetry which are associated with your third generation top quark.
Okay, but there's some degeneracy. In terms of the number of modes, they transform in the representation of
So
G,
so
and they transform in the representation
in
of G,
this model, it's
GL.
completely based on the G mod H. There's no additional degeneracy or something. But anyway, so that if you are interested, there is a twisted mode. So I have to load this gauge and they incorporate everything UV complete. That's what I can say.
Okay, let's thank Jing again.